o'clock. Hi, good afternoon, all of you. Please, if you are not interested, just leave the hall because the lectures are being recorded and whatever you are murmuring all will come into that, right? So I request you once again, if you are not interested, you can leave. But if you are inside the hall, please be silent because the lectures are going to be recorded and they are going live, right? Okay, thank you all. So I'll be just supporting the foreign faculty, Professor Ravi Mahapatra, in a few lectures, and he is the main architect of these things, and I am only a support for him in these lecture schedules. So I'll be talking on the sensors, actuator, and interfacing a little bit at the lower side. We'll follow that later on with the afternoon lecture. So I will just try to discuss on some of the issues on problem areas and design concepts and introduce a little bit of IoT in a different way. And for that, we try to see how to pick up a sensor and an actuator. And then we try to look into how to interface them to the devices. And then we'll see some application on that if time permits. So if we try to look into the problems what we have currently, there are a lot of areas where we can think like IoT can play an important role. And you can see that we have a lot of wastages going on in case of vegetables and fruits because they don't have proper storage systems and no transport facilities and no proper pricing. So all these fruits and vegetables, if you try to see the market, they just throw it off and go at the end of the day, and they cannot be reused because they get spoiled. And similarly, it's not only vegetables and fruits, we have a number of such type of things, like even if you try to see the cooked food in the places of parties and all, a lot of foods are being wasted, even in hostels or even in some areas where they donate food and all. There also we'll see lots of food is being wasted, and it is approximately around 20% of the cooked food is going waste. And garbage bins, if you try to see, they are not being cleaned daily basis. 50% of them are still having trouble. And we have even the drainage systems, and we have the transport systems. If you try to see, there will be mad rush at the bus stands and railway stations and everywhere. And similarly, we have drinking water shortage problems because most of the taps, if you try to see, they don't have the heads and it is not closed, and they spill over even if you want it or don't want it also. And even in the case of street lamps, you will see a lot of street lamps are not glowing, or they might be glowing in the daytime, and nighttime they are not functioning. And there might be some street lamps which are not functioning, they are not being repaired, and so on. We see a lot of such activity. Even in case of the activities such as paying the bill, going to a misava, or going to some worship place and all, you'll see a lot of large queues, then you stand in the queue hours together to do the job. And these are some of the areas where you can see that IoT will really help you in solving a lot of problems. Okay, these are only a few which I have suggested it. There might be a number of such type of problems in daily life. So if we try to look into those problems, we really get beautiful solutions out of it, which can solve those things in a more effective or efficient manner. So now let us look at a few solutions, and then we come back to the interfacing part. So now let us look from the design thinking methodology part. Just something like this is the problem, this is the solution and all. We will not go into that type of situation. We will see how to solve a problem given some type of real problems, right? Let us take one example of a routine activity where in every household, if you try to see, every weekend or after 3 days or 4 days, everybody try to buy something from the market and try to fill it up into the refrigerator or storage places. That is a routine activity in every household. It is not that exception. Some will not do it, others will do it. Right? And if you're trying to look from that point of view, and if you're trying to look carefully, every day what we try to do is we look at the refrigerator, and if eggs are not there, we buy eggs. If milk is not there, we buy milk. If vegetables are not there, we buy vegetables. Or some whatever is missing, we try to buy them and fill it up so that we can use it for a larger time. Right? For 1 week, some people might be planning for 1 week. Some might be planning for 3 days. Some might be planning for 4 days and so on. Depending on their requirement, we buy it and fill it up. So particularly if you try to see such type of problem, we have a refrigerator and a human in between who will check up what is there missing in that, and we go to the marketplace, buy them and fill it up. This is a regular problem which everybody have that. So here if you try to look carefully the problem, the human over there, he is not trying to do extraordinary work, a simple logistics, he is trying to see what is missing, going there and buying it and come back. Right? So you don't need a very expertized person sitting over there to do such type of job. Right? It is a regular routine activity, whichever is missing, we are buying and filling it up. So when you have such type of problems, like a simple problem like checking up, filling it up, you can give it to some other product or some product which can do that job, instead of a human being sitting there analyzing it and solving it and all, right? Because they are routine activities. So what we try to do is, nowadays we get online. Instead of marketplace, you can just place the requirements in the online, they'll deliver it and you can fill it up. You can reduce that activity because already online stores are available to us and we can easily place the order because we have cyber world along with us. So here I am using two words called as physical world and a cyber world. And earlier they are different, but now there is no difference between it. You cannot find a person sleeping without a mobile phone, right? So it is part of your life. Earlier it is a separate entity, but now those two have very thin separation between the physical world and the cyber world. So now we are not that much interested in cyber world or physical world because everybody have a mobile, everybody some access to the network, so you can get into that. So whether it is an online store or marketplace, a human being over there is trying to do a little bit of calculations and then getting it back to the refrigerator, filling up the refrigerator. And the problem is very simple. It is not a complicated problem or an engineering problem to solve it, optimize it, right? So if you try to look it carefully, I can replace the human being by a device called Internet of Things if this resembles the same thing, whatever the human being is doing. And we name that as Internet of Things, right? The job what earlier a human being was saying, if I can put that into a box and call it as Internet of Things, the problem is solved. Right? So now what I try to do is, I'll try to push this box into the refrigerator. I'm pushing that box into the refrigerator and calling that refrigerator as a smart refrigerator or IoT ready refrigerator. Right? And it can be refrigerator, it can be fan, or it can be AC, or whatever you. Right? I am pushing this box, what it is replicating the human being, and pushing it into refrigerator and referring it as a smart refrigerator. So now, if you try to carefully look at the box, what I have referred it as IoT, you can divide that box into sub-blocks where it consists of sensors and actuators, a signal processing and interfacing part, and a microcontroller or processor part, a communication module, and to power all these blocks, I need a power supply. Right? I have broken down the Internet of Things into a sub-modules so that we can understand it much better. And I divide it in such a way that the sensors and actuators as one block, signal processing and interfacing as one block, processors as controllers in one block, and communication, so that they can be understood very simpler. So now let us take yoga exercise, a second example. The first example, we have seen it very neatly, that it is very simple. We can divide in blocks, we can implement it. Now when we come to yoga exercise, somebody has to tell us the yoga time. You do 10 steps, you do 1 kilometer walking, you jog for 5 minutes, and so on. And we have to do that in a regular fashion. So now let us assume that a physical world is there where yoga is there, somebody tells the human and human does it. But now, in this application, if you try to look at very carefully, we are not going to replace the human being by some instrument, because yoga has to be done by us, not by the instrument. Right? So the design is not simple as what we have seen in the earlier case. And all the IoTs don't have similar design structures. Right? I hope I am trying to create it very simpler. All the IoT designs are not identical. Some might be using it to replace human beings. Some might not be used for replacing human beings. And this is very vital in our designs. Okay? So here, the yoga has to be done by the human being, and he has to have some set of duties or parameters which has to be solved while doing it. So when you do yoga, the doctor or the physiotherapist or the sports person will tell you, every day you take 100 steps or you walk for 1 kilometer and so on, but they are not ideal, because it depends on the human being who is doing the exercise. The parameters such as his BP, his temperature, his age, everything matters. So one day he might be physically fit, second day he might be having some problem with the stomach or leg or hand or something like that. So he need not have to do the same count. So there should be a equipment which tells me exactly how many I have to do, and that is what we call it as Internet of Things, right? And we refer that instrument as a wearable device which I wear it on my body and tells me exactly you walk only for 500 meters today, not 1 kilometer, because you have fever and you cannot do that. Or I have cold, so it should tell me that I should not swim today. Right? That is what the IoT of yoga means. So we cannot push the same ideology or terminologies and design concepts for both the cases. Right? So here we have a wearable device which tells the human being what yoga he is supposed to do. And that is controlled by a Bluetooth device or mobile, and it is also connected to doctor, and the doctor will look at your parameters and say, okay, stop doing yoga because your parameters are exceeding your heartbeat and all this. Okay? So the design concepts of IoT, we will not be able to see as a single entity. You have different ways of looking into the problem, and each problem demands a separate type of design. Right? So now let us move on to a third example. So the third example is a fire alarm system where a fire has to be detected and it has to be informed to the fire station so that they'll come and put out the fire. Right? So in this case, if you try to see carefully, so whenever there is a fire, a human being will try to see that. He takes his mobile and calls up and says that there is a fire to the fire station, and they'll come, they'll ask you exactly the location where it is, and they'll come and put out the fire. So that's the regular activity what we generally follow. Now we want that activity to be shifted to the IoT. Right? The example is clear. We have a fire detection system, like there is, whenever there is a fire, we can see without it. We can see that the fire is going out of limit, so you take your mobile, call the fire station, and they will come and they'll switch off the fire. Right? So when you are trying to look from this example, and let us assume that we want to shift this activity to IoT application. And now there are like 10,000 houses in a colony. And if you take, instead of that, if you take a 9-story building and each floor has 5 apartments, so 9 into 5, 45 apartments are there. So the fire station should know exactly which apartment it is and how to come to that apartment within a short period of time so that he can control the fire over there. Or if there are 10,000 houses in a colony, he should know exactly from which house the fire has started, and the person has to land up in that position exactly so that he can stop the fire. So now the design of IoT has shifted from simple blocks and then wearable device to something else. Now the data coming into the fire station house is like 10,000 data are coming in. I have to find out exactly where the fire is from the 10,000. For example, each sensor is sensing 8 bits, 10,000 it is 80,000 bits I have. I have to pick up which bits are troublesome. So it is not a simple task like what we have seen in the earlier examples. Now I have to see the anomalies of these data patterns and then react to that. Right? And it is not sufficient if the sensor data is sent to me, because the sensor data has to have an address to it. Right? And the address part is something like, just now a professor has told, IP6, 128 bits is the address. Right? So now you can see how the data size have grown up and it is becoming uncontrollable. Every second I am getting so much data to me, so that I have to react to it. Because I cannot collect hourly data, I have to collect every second. Because the fire has happened, if I collect hourly, by 1 hour everything will go to ashes. So I have to correct in a regular fashion. The data which is coming in is very huge. I have to store somewhere, process it, and take the next set of data, store it, process it, again take next set of data, and it is a continuous thing. Every second I have to do it. And if you try to do that on your laptop or your desktop, you will run out of your space. And the processing power, what you are trying to use on your laptop and desktop, is not sufficient to compute and say exactly this is the point. So we have to look at a bigger processors and a bigger storage space where we can, and that is what we refer it as a data lake. The lake is getting filled up with data, and we have to find a way to see exactly from the lake how to pick up the fish and use it. Right? So now there is no other go than to land up in the cloud servers where we have plenty of space and the processing power so that we can do this operation in a much faster way. Right? So now I call that a name different from Internet of Things, called as cyber physical system. Right? I'll refer that as a cyber physical system, and that has a cloud. All the 3 blocks what I have earlier, I pushed it over here, and now you have a cloud, and on the cloud you have data coming in. So I have to do some process to eliminate useless data and keep only useful data, because if I go on keeping all the data will be full. So I just useless things I can remove it and keep only the useful data and do some analytics on that, do some processing on top of it, and then I'll use machine learning to make a decision whether the data is useful or not, right? Or how to apply for a given application the data set. And that is what we are trying to look at the cognitive radio IoTs right now, right? And for power, this is a sensor which checks on the light intensity, and it puts on the bulb or switch off the bulb, right? So you can see that the bulb will be glowing up and down depending on the intensity of light of the sun, and that tries to put it on. Okay. So now from this simple task of connecting devices and all, we move on to the second generation one, where it gives you some connectivity to the world, where you can know what is happening in my hometown. It is not that it is happening here. I kept the device in faraway place, and I'm trying to monitor from here. This is what we refer it as a second generation IoTs, or the second level of IoTs, right? So we have connectivities. It can be a wired or it can be a wireless also. It is not that only wireless will do. It can be wired communication or it can be wireless communication also, right? And after this, we move on to the next level of IoTs, where we refer it as multiple devices, like 10,000 devices we have to handle it, right? And still, this is something like still manageable. If I have a control station over here, all the apartments are connected, I can easily monitor it, right? Or if I have a laboratory and I have different sensors in it, I can still monitor it. I don't need any data analytic on it. So this is what we refer it as a third generation, a third level of IoT designs, where you have multiple devices coming in and they can communicate among themselves, right, without our interference into it. So for example, if you try to see, we have some hospitals are running it, where they have their beds connected to IoT devices. They have some machines which are connected to IoT devices. There are some labs where they check these blood, glucose and all, they are connected to it. So the doctor knows what is happening with any patient over there. That is the next generation one. We are not doing anything highly analyzing it and so on. Okay, simply connecting all the devices to the servers and we are trying to monitor it. So the next generation, if you try to see, we are trying to integrate the cloud, IoT and the AI. And this is where our course right now is trying to look into it, cognitive Internet of Things. We have three dimensions in this problem. One is the IoT, and the second one is the cloud, and the third one is artificial intelligence, which we are trying to integrate it so that we can create intelligent and independent systems that can learn, justify and interact with humans directly, right? So that you can speak and find out what is going on. So you can say to the device saying that, so like I hope you all know Siri. Siri, tell me the way how to go, right? I hope you might have using it. So it will tell you the location and in your own language and with your own impressions and everything. It can read it out and it can interact with you and you can get it to that. So this is a little bit of introduction of Internet of Things. So we can conclude something, summarize it something like, the designs are very critical and they are not identical. And each IoT design have to view it in a separate fashion. You cannot generalize everything into a general design structures. And we are moving out from the first phase of IoT to second phase to third phase, and now we are currently into the fourth phase of IoT designs, where we are trying to look at from a high level of integration from cloud and IoT designs and the cognitive or the AI coming into picture. We call it a cognitive computing, which is a central place where it gives us a better feel or the systems as if they are talking to us. We can say, tell me what is happening with the patient. It will tell us everything. Then I can say, okay, you react to him, give him this tablet. The IoT device will give the tablet to the patient, right? There is a robot. So now the robot knows exactly how the patient is, and it tells to the doctor saying that the patient parameters are these. So based on that, the doctor will advise the robot, give this tablet, the tablet will be given. Or something has to be taken care, it will do it, right? So the examples of cognitive IoT, if you want to see, the robotic surgery is one of them. Or the automated vehicles moving on the road is another example. They have to compute and then they have to tell how the next vehicle, whether they are coming closer or they are going far apart, all these things have to be calculated. So when we say cloud, don't assume that cloud is somewhere high and all, because what happens is when you are trying to transmit the bits from here to the cloud and getting it back, the latency plays an important role. The latency means the delay what it takes to go up and come back plays an important role. So if it is very far away, the time taken for the bits to go from one end to the other end and coming back, it takes longer delay. Suppose there are 3 robots which are doing an operation on a patient, right? And the one robot will send the data to the cloud, compute it and get it back. It takes few minutes, then the patient has to be wait there for the other robot to interact, and it takes longer time and the patient might die. So we want a lower latency type of application where instantly after one robot, the second robot will take up the robot and they try to coordinate and finish off the surgery. So in such cases, the latency have to be very low, which means that we have to bring the cloud down to a lower level so that the latencies can be reduced. So now we define that as edge computing, fog computing, and the cloud, right? So at the edge only we try to compute it and give it to that so that the latencies can be reduced and we can get a better output. For example, you are driving a driverless car on the road, you cannot wait for a few minutes to get an instruction and then you'll move, right? The time taken for computation should be as small as possible in microseconds so that you can react. Because even if you are moving at 100 kilometers per hour, if you boil down to a second, it comes to a few meters. So within a second, you hit by 100 meters or 50 meters, you will hit it, right? So your computation has to be very less than a second also. You don't have that luxury to spend so much time and wait for the result and then react, right? So the computation has to be at a faster rate with a low latency, and hence we are trying to push it down reduce the distance of the cloud and calling it as edge computing. The computation will be done at the edge only, and then they get the result so that they can interact, right? So this is one way of looking into things. The second way, if you try to look at, we need a different type of environments for some applications, right? Professor, you will be teaching again the IoT structures and all. Okay. Yeah. So you are going to, these parts you are not getting it. Yeah, okay, that's fine. Yeah. So what we try to do is we spend some more time on understanding these applications of cloud and the AI and IoT, how to integrate them for different applications. And then we actually get into the interfacing part, sensors and interfacing part, because I will continue with the sensors and interfacing. I'll take the questions later on. So if you try to look at the sensors and actuators which we try to use for integrating into the hardware and all, before that, let us look at, you have an automated driverless car, and to carefully look at the number of sensors in that car will be around more than 100 sensors will be there in the car. It is not 1 or 2. And the actuators in the car will be also equal to 100. So if you are trying to look from that point of view, there are 100 sensors which you are picking up different parameters of the car, and there are 100 actuators which are trying to solve the problems inside the car, act on the car for opening the door, closing the door, air pressure increasing or decreasing, and so oils, whether it is increasing or decreasing, all these things if you try to see, they are monitored in a continuous fashion. It is not that once in a while they try to monitor. And it's not only that, it also have to look around the environment and tell where is the next fuel station, whether the fuel is sufficient to drive up to that point or not, and whether the air pressure is good, otherwise where is the next air point where he can fill it up, or there is a charging point where he has to go and charge the car. There are a number of environment parameters also it has to monitor. It's not only just sensing the parameters of the car. So if you try to see the complexity of the design, there are not few sensors to few actuators. There are something like hundreds or 200 sensors you are trying to monitor it, and you are driving it 200 actuators at it. So even if you calculate the time required for each sensor data and so on, it should be in the order of nanoseconds or microseconds. You cannot have a luxury of, you cannot say that I'll monitor every sensor for 1 second, next second I'll do another sensor and so on, because only you come back, it takes 100 seconds back again to the first sensor. And 100 seconds is sufficient, it is 2 minutes or 3 minutes, so you will be lost in the way. So please remember that we don't have luxury in our design. We have to struggle to see that the things are running at the right direction, right? And this, as a human, we can do it, but after some time we find illogic, something like a routine thing, it's okay, we can leave it. So we will not take those errors into our design. So we push it up to the machine to do it so that it can remove all these human errors and design it properly. Okay? So that is another part, important thing. We have to see that the designer doesn't have any luxury in designing the complexity. We have to somehow see that the machines try to do it at its peak so that we get the best result out of it. So now coming to the sensors and the actuators, we have to pick up the right sensors and the right actuators. That is the prime goal of the topic. And we need a right interfacing circuit to the given application matching. Whatever the application demands, we have to design our circuit such a way that the parameters are met with. Otherwise, the outcome will not be the desired outcome. So the process is not simple that one cycle is sufficient. We might go through number of cycles to get back to the right answer. Okay? So the designing part, we have to be very careful, and we have to pick up right design parameters. So we know that we have different types of sensors like a human being. We can see, we can hear, we can taste, we can smell, and we can touch. All these are there in our human body. We can do it. And if you try to look from the design of the human body, we have a brain as a processor, and all these things are connected to the brain, and they are doing the processing instantaneously and tell you. It is not that it is telling you after 1 day, right? The brain, immediately when you touch it, you know that there is some shock in the machine or something. It is not that after 1 day it tells you, right? And similarly, if you see something, it tells you immediately this is what you are seeing. It will not say that I'll take 5 minutes to tell you the answer, right? When the human brain is so much designed such a way that all the parameters what it takes in the live, you are getting the instant outcomes out of it. So we want something like that to be mimicked in the circuit so that it does such type of operation. And that is what the cognitive computing is. They have to compute at a much faster rate and then come out. And if you try to look from your architecture like your CPUs and all, it will not be able to do that fast, right? I think most of you might be playing games and you don't pick up the CPUs, you want NVIDIA GPU or something to react so instantaneously for your gaming process. And we need something like that for making a decision of instantaneous outcomes and so on. So now, if you want to put this into an electronic form, we have optical sensing. We need some optical sensors to capture the vision and all, like your cameras and all, right? And you need acoustic sensors for hearing it, and you need chemical sensor for smell and taste, and you need mechanical sensor for tactile, and some touch pressure sensors for touch and all. So the outcome of that is there are different fields which are coming in. It's not that one field will solve all the problems. The chemical people are trying to give their best, the MEMS people are giving the best, the mechanical people are giving the best, the electrical people are giving the best, electronics people are giving the best, and computer science is adding up and building up the best, right? So don't assume that the IoT belongs to a particular department or a section. It is everybody's property. It is not only ECE property or computer science property or something. Everybody in these, all the streams, either it is a mechanical or a law or a humanities or arts or science, whatever it is, everywhere it is connected. And that build up the smart cities or smart hospitals or smart laws, anything you name it, you'll get it out, right? So please remember that there are different types of sensors which we are trying to look at. And we can define the sensor as a device that responds to a physical stimulus as heat, light, sound, pressure, magnetism, or particular motion, and so on. There are a number of things. And transmits a resulting impulse so that we can have a measure of that parameter, right? And that is what you get it from Webster New World Dictionary, right? So this is a dictionary definition only. It is not invented by me, but it is used by me. Right? And it is very clear. It says that there is a stimulus, and that stimulus, when applied, responds, and you get some type of impulse. It can be electrical impulse or mechanical, whatever it is, which can be measurable, so that you can connect some actuator or some device so that you can get the outcome of it. And actuators, if you try to see a mechanism or some moving object, we refer it as actuator. Either you make the switch on and off, or you drive a motor, or you make the bulb glow and off, or you increase the sound and decrease the sound. Whatever it is, you are trying to displace it, which may be linear, non-linear, up or vertical or horizontal, whatever it is. A change can be noticed by the actuators. Right? And we define that in the simple terms, the reverse operation of the sensing part is actuator, and which means that we provide the electrical input and we get the physical action. The physical action is movement of anything. Okay? So this is one important thing, the sensors and actuators, and I'll stop over here, Professor, because 12:45, because they have to walk down to the. No, I can take for some more time, but okay, I'll give one example and I'll stop it. So I'll give one example of what actuator and sensor and what water tank means. Suppose you have a water tank in your house and water is filling up. When it is at the brim and overflowing, you switch it off, right? I think it is a common example in each and every house. Whenever you have a water tank and you are trying to fill it up, water is coming to the brim, you will just switch off the motor so that it will not overflow and all. So in that process, if you try to look the example very carefully, you can see that we have a sensor, we have a processor, and we have an actuator. So the sensor is nothing but your sight tube and the optical nerve, which tells that, okay, the water has came up to the brim, and automatically your signal is sent to the brain, and it starts processing, and it automatically lifts your hand and put it to the switch and make it off. Right? That's the phenomena what we are trying to capture it, and we are trying to put it into the design of IoT things. Right? We have the sight tube and optical nerve, which tries to observe the filling of water into a tank, and as it comes to the brim, the brain processes that events and try to say that, okay, now it is full, you go and switch off so that you can see that the water is not wasted. Okay? So this is how the process runs even in IoT designs. It is not only the human design, but even in the IoT designs also we try to mimic the same environment so that we get the best output from that. Okay. So I'll stop over here, and we'll continue in the afternoon at 2:30. We have a lecture from 2:30 to 3:30, and then followed by the lab session from 3:30 to 5:30. So if you have any questions, I can take it up for a minute or two, and then we can proceed for a break. Yeah. Sorry, sir. Yeah. Actually, I have stopped over here, and my next slide is that only. Yeah. Okay. It is not one-to-one. It is many to n to m. It is not n to n also. It is n to m. Both are independent. Yeah. Any questions? Okay, thank you all then. Right, we'll meet at 2:30. And I request the participants to contact Harishma for the, you are giving the coupons?